Thank you. So first of all, I'd like to thank the organizers for having me here. Well, when I gave my title in abstract, I gave a very vague title, but mostly I'll be talking about cominuscule variety. So that is in some ways the dual of the previous talk. So what I'm going to talk about is joined with either Constance-Rich or Constance-Rich and Lauren Williams. So I'd like to start with an example that we're all presumably very familiar with to give you an idea of the point of view I'm going to be adopting. So let's look at projective space. So we all know that projective space has a mirror that's a Landau-Ginzburg model. So it's a pair. X check. Well, let me write it like that. W. So X check is a torus, same dimension as the projective space, and I add something for a variable q, and W q is x1 plus etc. plus xn plus q over x1 times xn. So we saw that already in the previous talk, and that's known as the LG model, Landau-Ginzburg model for projective space. So I'm going to repeat in a little bit more detail. One of the first things I'd like to have when I'm talking about a mirror. So first thing is that I like to have an isomorphism between the quantum cohomology of X, so quantum cohomology of projective space, and the Jacobi ring on the size of the LG model. So quantum cohomology of X. So here I'm talking about the small quantum cohomology. So just same setting as in the previous talk, so I'll have just one quantum parameter. So that's the small quantum cohomology. And so I will need to localize this at the quantum parameter, and that will be isomorphic to the Jacobi ring of the mirror. So which is defined as C of x1, so parameters of the torus, x1 to xn, then we've got q, and we divide by the differentials, so dxi of wq. So here it's is that too small? It's very concrete. Here the small quantum cohomology, so we all know the cohomology is generated by the hyperplane class. If I want the small quantum cohomology, I add the quantum parameter, and of course that's the relation. And this Jacobi ring, well, it's just this, and this. This is the same as quotienting by the relation, so saying that xi is equal to q over x1 times xn. Okay, so for all I. And of course, if you map the hyperplane class here to, oh yeah, so I need to localize. So if I map H to either of the xi and q to q, that gives me the isomorphism. So that's very clear what happens in the case of projective space. And the next level is looking at vector bundles with connection on each side. So here we have the Dubrovin connection, on that side the Gauss-Manin connection. So I have, so it's a trivial vector bundle. So with fiber, I have the cohomology of my projective space. I have the quantum parameter, and I have, well, let me omit the other direction. So this is my A model connection. So trivial vector bundle with fiber, the cohomology, and connection as we saw is QD over DQ plus H, so the hyperplane class, and then this denotes the quantum product. So quantum multiplication, so the multiplication in the cohomology ring. So from the other side, so we have the Gauss-Manin system. So here we look at the twisted de Rham cohomology. So for X check, and we twist, so instead of just taking the usual differential, we twist by the superpotential, and this goes over C star Q, and the B model connection, so Gauss-Manin connection, is so same term, so Q dDQ plus, and then we just take the class, so we multiply our form by the superpotential. And so what happens here is that the mirror is so we can easily here describe the map that we expect should be the isomorphism, because this X check is a torus. So of course there is a canonical form, the x1 wedge dxn. And if we want to construct a map, so I'm constructing it on the level of well, the fiber here. So to the ith power of the hyperplane class, I can just associate this times product x1 to xi. Okay, and so it's the kind of thing that one may want to emulate for more general homogeneous spaces than projective space. Okay, so I'm going. So to go towards that, at least in the case of cominuscule homogeneous spaces. Sorry? Oh, the bracket here just means the class of, yeah. Well, I could remove it if, but I just want to say that we need to multiply by something. So okay. So as in the previous talk, one main motivation is the result of Constance Rich from 2008, where she constructs the theoretic mirror, or mirror candidate, depending on your point of view, for homogeneous spaces. So by that I mean that she proves this in her 2008 paper, but not this. Right, so the construction, so X is any G mod P, so no assumption about P corresponding to a minuscule, co-minuscule weight or anything like that. So you take the usual Borel, parabolic, the maximal, whoops, yes, no, take the Borel, the maximum torus, and right. Okay, so that defines us, well, everything we need to be able to talk about Schubert cells. And so the mirror for X will be defined on a Richardson variety in the Langlands dual flag variety. So I take G check the Langlands dual group of G. So G my semi-simple algebraic group over C. Langlands dual essentially does nothing if the group is simply laced, so just changes adjoint into simply laced and vice versa. We'll see examples, so I'll talk about Lagrangian Grassmannians, where here it does something quite a bit more drastic. But anyway, so the mirror is an open Richardson variety inside. So that's the original version for the mirror inside G check mod B check. So that's the full flag variety with respect to the Langlands dual group. Okay, so maybe we can give a little bit more detail. So I denote by W0. So inside the Weil group of G, and WP inside the Weil group of the parabolic, so Weil group of P, the longest elements. Actually here I should take the opposite, doesn't matter very much. And that Richardson variety is the following. So the intersection of this open Breuer cell with another cell corresponding to the opposite Breuer group here. Okay. So that's how it is defined. So it's nice to see it like that, because then we have results from Geis, Leclerc, and Schröer, which tells us that it has a cluster structure. So coordinate ring is an upper cluster algebra. But it's so if I want to express the superpotential that was introduced in the previous talk, I have to use the isomorphism that was mentioned there, which is that this is in fact isomorphic to the following. Well, bit of a pain to write, but okay. So basically, I write it as this intersection here, and my point is that I can parameterize this using an upper unipotent matrix and a lower unipotent matrix. So U1 T WP U2 bar, and of course there are conditions so that this together belongs to that. And so once I've done that, so the superpotential that I'm going to introduce, defined by Rich, is just taking, well, the idea is just taking the sum of the upper diagonal coefficients here and the sum of the lower diagonal coefficients here. Of course, what I say would be true in the case of GLN. It's a little bit different in general, but you can still define Fp of such an element as the sum Okay, so these are the Chevalier generators, and that roughly corresponds to taking coefficient just above the diagonal or just below the diagonal. And what Rich proves so it's via the Peterson isomorphism, but I won't repeat that here. So proves that the quantum homology of G mod P, once properly localized, is isomorphic to this Jacobi ring of R check W0 WP and FP. Okay. So in the minuscule case, in the last talk, we saw a good way to study this issue with the connections. Here I'm going to present another point of view that is more suited to the minuscule case. So my first goal will be to find some nice projective coordinates for the mirror. So reformulate all that in terms of projecting that on which leaves a priori in the Langlands dual full flag variety to the Langlands dual partial flag variety, and find some nice projective coordinates for that make this isomorphism here easier to express, and that's something that we can do in the minuscule case. Okay, so the first thing to do is, well, quite natural. So I have a priori my Richardson variety that lives inside G check mod B minus check, and I want to project it to G check mod B check. So basically, P check, that's defined. So if I have some series of weight defining me P, I take the dual weights, and that defines me P check. We'll see concretely what that means. And so I have, FP here, and I will just, project that here. So from Knudsen, Lam, and Speyer, we know that these varieties, so this specific one, not any Richardson varieties, but these ones project isomorphically onto So that's because of the choice, right, of the Weyl group elements here. That's project isomorphically. So like it's isomorphic to its projection on here. It's and also it is a log Calabi-Yau, so the complement of an anti-canonical divisor. So I check to be projection. No, that's not FP. That's phi. The projection of this, and so it's isomorphic this, and it's smooth, affine, dense. So dense in G check mod P check, and log Calabi-Yau. So in particular, that recovers the point of view of Gross, Hacking, Kiel, Kontsevich, even though I don't know if it's already proved that the constructions really are identical. But certainly that's the same framework. Okay, so now I'm there. So I've got my mirror that's contained in there, and I want to find some nice coordinates. So let me look at the projective embedding into, well, natural projective embedded given by the representation of G check corresponding to the weights defining P check. And now that's where it's nice to be in the cominuscule case, because there is the geometric Satake correspondence that will tell us why these coordinates in the cominuscule case are particularly nice. So let me first maybe say what cominuscule means. So I won't define it, I will give the list. So we have cominuscule homogeneous spaces in the following types. So I will give the adjoint group here. So PSLN plus 1. Here SO, and 2n plus 1. PSP, so in type CN, PSP 2n, type DN SO2 and PSO 2n. And here, well, the exceptional groups. The corresponding cominuscule space, so in that case, it's all the Grassmannians. Here in type Bn, we get the quadrics, so the odd quadrics. In type Cn, we get the Lagrangian Grassmannians. So that is well, Grassmannian of isotropic vector spaces of dimension n in a symplectic vector space of dimension 2n. And in type Dn, there is the even dimensional quadric and the odd, so Q2n minus 2, and the maximal orthogonal Grassmannian. And well, here there's the Clelia plane that was mentioned earlier, and the Freudenthal variety. So the ones that are not minuscule are these two. So these two are comminuscule but not minuscule. All the other are comminuscule and minuscule. Okay. So now, geometric Satake, what does it tell us in the comminuscule case? So this is due to Lustig in 95, Ginsberg 95, and Wilkowicz, Pilonen in 2007. So it relates the representation of the Langlands dual group with some intersection cohomology in the affine Grassmannian. So it's 85. Well, I take that from my paper with Rich, and she's her student, so I hope she's got it correct. But yeah. Okay, so yes. So in general, that tells me that I've got this representation of G check corresponding to the parabolic, and that's isomorphic to some intersection cohomology of a cycle. So in the affine Grassmannian, and what happens in the comminuscule case, so if P is comminuscule, then this is just the usual cohomology of G mod P. So what it means is that my projective coordinates here are naturally dual to the Schubert classes. I mean, I can choose them as naturally dual to the Schubert classes of my original space, which will make, well, which will give a natural identification, so a natural morphism between the quantum cohomology and the Jacobi ring. So, yeah. So the coordinates on my mirror X check are, well, can be seen as dual to the Schubert classes of X. Okay, so that gives a natural way to see, of course that's no proof at the moment, right? But a natural way to see the potential isomorphism. And also, since X-check is both log Calabi-Yau and also has a cluster algebra structure, these are twice the same way of saying, well, of seeing that you can find a unique optoscalar N form that's regular on the variety and has simple pole on the boundary. So, which will give you a hint as to what the map between the bundle with connection could be. So we've got some Schubert classes of X, which I will denote by sigma W. For W, the Weyl group of G quotiented by the Weyl group of the parabolic. And I have corresponding Plücker type coordinates of the dual, so PW indexed in the same way. And I have a canonical, well, so unique n equals dimension of X form on act check with simple poles on the boundary. And it's natural to expect that the map between the two bundles with connection will come from this. Okay. Right. So that's the framework we're working in, and then so in some cases we are able to do this. So Lauren mentioned the case of Grassmannian, where the result was proved by Marsh and Rich. So, well, part of the result was proved by Marsh and Rich. So what I'm going to do now is give some idea of what the constructions are. Maybe I'll go a bit quickly for the case of Grassmannians, because we've already seen it in Lauren's talk, but okay. So how's the mirror constructed? So I'm taking X to be GR Kn. So as was explained by Lauren, to parameterize the Schubert classes, or indeed the Plücker coordinates of the mirror, so the mirror, which will be so this is Grassmannian of k planes in C to the n, and this is the very, very different Grassmannians of n minus k plane in C to the n. So we can parameterize the Schubert classes. They are the Young diagrams with classes of X are the Young diagrams which are inside a k times n minus k rectangle. Okay. So this is all, yeah, I've said it, but I should write it. This is all resolved by Marsh and Rich here. And Lauren explained how from this data you also get the Plücker coordinates on the mirror. So there's a very nice way to remember how you can write the superpotential. So if we take, for instance, GR 25, so for the superpotential, so that's superpotential, so that's so it is my, so the FP I've introduced before, but as expressed as a function no longer on the Richardson variety, but on its projection. Okay. So among the partition contained in a two in a 2x3 rectangle, you have some that are maximal in one of the dimensions. So that they correspond to the cyclically ordered sets. So if you've got 2x3, you have Flickr coordinate corresponding to the empty partition, Flickr coordinate corresponding to this partition, so that's maximal in terms of length. So you take all of this. So if you take these rectangles, for Grassmannians, that's a rule always to obtain the superpotential. So you take those maximal rectangles, and then you see how you can add a box to those rectangles while staying inside the 2x3 rectangle. So here it's easy, adding a box to the empty set. Here there's only one way, otherwise you're too long here, so there's just one way. Skip this one for the moment. And here similarly only one way to add a box. So here there's no way to add a box, it's full, but you can quantum add a box using the quantum Month rule. So that means removing a hook and adding a quantum parameter. So remove the hook like that. Okay, that's the rule how to get the superpotential. You can, so this is this superpotential is a partial compactification of the Batyriev-Chokan, Fontaine, Kim, Van Straten, Landau-Ginzburg mirrors for Grassmannians. So you these mirrors, the way they go, you draw a graph. And so these are toric mirrors, so you put some coefficients, 1, Q, and here toric coordinates, so I don't know, 1, 1. Okay, so you use for each arrow, the superpotential is given by sum over arrow of head of the arrow divided by tail of the arrow. So oh, this is Batyriev-Chokan, Fontaine, Kim, Van Straten mirrors. Okay. I thought yeah.
So can I just clarify? I mean, is this an instance of a Horry-Buffer mirror for a toric Fano where we take the torus to be the specified maximal torus? Or
By this you mean this or this?
The top.
This is not toric.
This
This is not a Laurent polynomial
so
because of the Plucker relations.
So what is its meaning?
Oh, this is just I've just given the formula for this as defined by the Plucker coordinates. So this you can embed into projective space. And you've got some Plucker coordinates. I've chosen to index them by Young diagrams. So instead of indexing them as you may want to do by subsets telling you which minors you take, I index them, which is perfectly equivalent by Young diagrams, so that you can see more the why it corresponds to Schubert classes.
But I still have no idea of what the underlying. This should be sort of, in principle, this should be counting holomorphic disks on some Lagrangian torah. I mean, what's what in principle is in the background of this.
So this, for instance, will have as many critical points as the cohomology of the the dimension of the cohomology of X. So that's why you may.
In some cases, it can be shown that if you take this corresponding you can degenerate to a toric variety, and then this function can be followed along, and then it does become a Laurent polynomial, and it's the Horry-Vaca potential of that toric variety. So
yeah. So this one comes from toric degenerations. I think that's how they construct it. And this one is a partial compactification of this one.
Okay.
So I will explain how you can relate those two. So this is a partial compactification which has the advantage of recovering some of the potentially missing critical points. So because in that one, even I think it was noticed by Eguchi, Horry, and Xiong, that even for GR24 you don't get enough critical points. I mean, not as many as you would if you use this style of mirror.
That's what the partial compactification.
Yeah, and here when you do this partial compactification, you recover them. Okay. So yeah, so let me. So since this one is probably more familiar, let me explain how you relate them, at least in the example. So you just replace this by, so this quotient, box over empty set. Here you take the two boxes. Okay. Can never remember those ones. Yeah, 2 boxes over 1 box. And then 3 boxes over 2 boxes. And here this is still empty set, 1 box. Anyway, it's probably correct by now, but in case, even if it isn't, so there's a general rule that you can use to recover that they are the same, and if you use the Plucker relations, you recover exactly this. Okay. Right, and so what Marsh and Rich prove? Maybe I'll keep that for a while. They prove that if you take this mirror, so assigning sigma lambda to p lambda canonical form defines so an injective homomorphism of bundles with connection. Okay, so that's from 2013, I think. So, why injective homomorphism and not isomorphism? That's because the way they do it, basically they use heavily the cluster structure on the mirror, so on this X track, so that they can see that the connections, well, are preserved. Injective is not to see that you recover the whole Gauss-Mannian system, you have a problem in that you need to know some properties about the superpotential that we don't have. So things like homological tameness. So the way they do it is, well, that's what they would need to do. So we saw in the previous talk that they were around it using these automorphic forms. But yeah, so that's the result that they obtain, and that's the the kind of formula they get. So now I'm going to talk about quadrics. So quadrics, they occur in type Bn or in type Dn. So the odd quadrics, I looked at it with Constanza H, and the even ones, well, we also talked a little bit about the odd ones here, but with H and Williams. So here the situation, well, given Tal has constructed mirrors for the quadrics, so what's the difference, one may ask? So in some cases, the mirrors don't recover, so same issue as before, the historic mirrors don't necessarily recover all the critical points. There's generally one missing, and that's the construction here will recover all the critical points. That's actually a consequence of the construction of Rich, that you always get all the critical points. So let's see how it works. So the odd quadrics, let's look for instance at Q5. So Q5, the cohomology, so you know that you have one cohomology class in each dimension, so let me call them sigma 0, sigma 1, sigma 2, 3, 4, 5. Then for the mirror will live, so it will be X check inside, so that's my X. Mirror just lives in projective space, 5-dimensional projective space, so it's very easy. And so the way you define the superpotential, well, so here, it definitely doesn't look like a Laurent polynomial this time. So it's maybe more convincing that it's not the same as the better known mirrors. Well, I put P0 to 1, right? So that's why. So I've got these quadratic mirrors. You can see how they're constructed. And on top, I just take, so there's just always one term that you can easily guess how you obtain it, right? Okay, and what's interesting is that in this case, the cluster structure on the mirror is very easy. So I can draw a quiver. So on X check, we've got a cluster structure of finite type. So that makes looking at the connections much easier. Finite type. So if you want to look at the quiver, you've got some cluster variables and some frozen, so I would put them in a square, some frozen variables. So I've got P5 here. So this is all frozen. Okay, and if you mutate that, you will change P1 into P4 and here P2 into P3.
So what is the base on writing this function here?
So you mean the?
But how do you get? What is the meaning of this function?
Oh, so P0 up to P5 are my projective coordinates here.
And you just wrote down the formula. So what?
Oh, how you mean how you get it?
Yeah.
Okay. Well, what we do is that first of all we use the definition with the Chevalier generator, so the usual of the FP. We use some parametrization of the unipotent cells. So so that gives us a Laurent polynomial expression. And then from that Laurent polynomial expression, we recover the PI. So the PI, you can view them as some matrix coefficients.
So there is supposed to be some Landau-Ginzburg potential function on the middle? Or?
That's the Landau-Ginzburg superpotential. Yeah. That lives on the mirror. That lives in here. Yeah. Okay, and here, well, that was just to give you an idea of the cluster structure. And in that case, we can prove the same as for Grassmannians. Okay, and I will.
Check is just the complement of where the denominators
Yeah,
are.
so it's just where P0, P1, P4 minus P5, etc. non-zero. Yeah. So, yeah, I won't maybe go into too much detail, but the even case is a bit different in that the mirror lives in a dual quadric, well, which is isomorphic to the original one. So here, if you have Q4 instead or Q6, the mirror lives inside a similar quadric, and you get formulas that are not very different, and cluster structure also of finite type, but just with an extra arrow to a frozen variable here. So even though they don't live in the same type, the structure is not so different. Now I'd like to talk about the Lagrangian, which is, as I said, an example which is really non-minuscule. So here what happens, so my Lagrangian Grassmannian that I defined earlier, so Lagrangian of isotropic subspaces of dimension n inside a symplective space of dimension 2n. This is, well, I can take my group to be PSPN, and then the mirror, if that is X, the mirror will live inside something very different, which corresponds to an orthogonal Grassmannian with an action of the spin group. And so here, if you want to express the mirror, it involves looking at the representation theory of the spin group, and we go via the cluster algebra to get the results. The formulas are a bit more intricate for the superpotential, but it's the same idea. We've got some terms that look quadratic. So yeah, I'll just give you an example, and then I'll stop there. So for instance, if we take LG3, the mirror will live inside OG3. So remember that for Grassmannian, the Schubert classes are indexed by partition contained in a k times n minus k rectangle. And here, Schubert classes are indexed by strict partitions, so no two equal parts in the partition contained in a n times n, so 3 by 3 rectangles. So you've got, so it's indexed by sigma lambda, where lambda is in 3 by 3 rectangle and strict. And similarly, you can define, so this, you can define corresponding p lambda, so some projective coordinates. And in that case, if I use those conventions, it's same idea. So here, if you want to understand this term, how it's constructed, you just stack you just stack those boxes one on top of the other to get this element here. And you do the same for the denominator with an extra box. So, well, the formulas in themselves, my main point in giving you the formulas is that you can see that it's quite explicit. Okay. And here it's a bit tricky because, well, if we want to look at the connection, so we can prove, of course, that this is the same. So using this Clifford algebra techniques, that it's the same as, so isomorphic to the mirror defined by Rich on the complete flag variety. But the cluster structure, so if you want to look at the connection, it's somewhat trickier because we're no longer in the simply laced case. But you kind of see from that example that there should be some similar things coming into play. All right, thank you.